Hey guys, today chapter 15 is our topic. Chapter 15 is about temperature, heat, and expansion. We're going to learn about temperature, how to measure temperature, heat, specific heat capacity, and expansion and contraction due to increase or decrease in temperature. Alright, temperature is proportional to the average kinetic energy of the molecules in any substance that you have. Increase the temperature, molecules start vibrating and shaking more, and then they expand more, and you have volume expansion. You change from a liquid to a gas or a solid to a liquid. All kinds of things can happen. This increase in energy is proportional to the increase in temperature. Well, we measure temperature with a thermometer. We probably already all knew that. Okay, well, you put a thermometer into hot water, right? That heat from the hot water is going to go to the cooler thermometer, right? Remember, heat always travels from hot to cold. So it's going to leave the hot water, go to the cooler thermometer, and then what's that thermometer going to do? The alcohol in the thermometer is going to rise up, right? Well, when does it stop? Well, when that thermometer reaches the same temperature as that water, when we have that thermal equilibrium, right, the same temperature, then the temperature will stop rising, the alcohol will stop, and that will be when you take your temperature reading. All right, we have 3 temperature scales: Fahrenheit, Celsius, and Kelvin. All right, we'll be mostly using Celsius. All right, and I've got some information about those here for your reading too. All right. Well, we've talked about how heat travels from hot to cold, right? Well, the reason why that's important is because if there's no difference in temperature, then heat's not going to move. There's got to be a difference in temperature. One's got to be hot, one's got to be colder. There's got to be some difference there for any energy to flow. Okay? Always. All right. Now, heat can be measured in joules, which we've used for energy before, or it can be measured in calories. All right, for example, 1 calorie is defined as the amount of energy needed to increase 1 gram of water by 1 degree Celsius. All right, and I've got some information for you there on that as well. All right, specific heat. Specific heat is how much energy is needed to change the temperature of a substance by 1 gram of a substance, by 1 degree Celsius. All right. Well, I just gave you specific heat for water. That's 1. Well, what if you don't have water? What if you have iron or alcohol or whatever? All right. That's where their specific heat comes into play. All right. Specific heats can be looked up in your book or online, but that's what it means: is how much energy does it take to increase that temperature? Okay. So how can we quantify heat? Right? Well, it depends on how much of a substance you have. Do you have 1 gram, 10 grams, 1,000 grams? What material do we have? Again, water, iron, mercury. What do we have? And then that difference in their temperature, that temperature change. All right? And here's the equation right here. So Q is for heat, M is for mass, lowercase c is the specific heat capacity, and then delta T, that's your change in temperature. Multiply those 3 together, and that will give you the amount of heat that is needed to do what you want to do, to increase that temperature of that much material. All right? Well, specific heat can change climates, right? It can determine how those currents move, how the wind blows and carries heat from continent to continent. Just a little trivia, little interesting facts, right, listed for you there. Thermal expansion and contraction, right? Well, what happens if you've got a piece of metal and you put it in the fire, right? It's going to get longer. It's going to expand, right? You put that same metal on a different day in a bucket of ice, it's going to contract, right? Because you're decreasing the temperature, which means those molecules are going to contract up. They're going to get closer and closer together because they're going to be slowing down, decreasing their kinetic energy. All right? So you're going to have contraction, right? Opposite's going to be happening when you have that piece of metal in the fire. All right, increase in temperature means more motion of those molecules, expansion, because they're jiggling all over the place and colliding, and there you go, you get bigger. Okay? Contractors, architects, engineers have to really pay close attention to this, or else you get something that looks like that picture over there. They didn't plan for the expansion of those railroad tracks in the summertime, and look what happened. Not going to be able to run a train on those tracks. All right? Well, there's also practical applications for this expansion. Right? Studies have been done and different metals expand at different rates. Right? This is useful because we can make a strip, a bimetallic strip, which means there's bi means two metals, one on either side of the strip. And they're going to have different rates at which they expand when heated. Right? This makes a difference because you can make a switch out of that. Right? Or a valve, or things like of a mechanical nature, because you heat it up or you cool it down. It'll work either way, right? And since one expands, contracts faster than the other, you will get a bend, right? And then that bend can flip a switch, all right? Pretty cool. Okay, now, almost all substances contract when they're cooled down, and they have a decrease in volume and a decrease in temperature because of that decrease in kinetic energy. Right? Of course, there's always one rebel that doesn't want to follow the rules. In this case, it's water. All right? Now, we learned back in chapter 12 that solids take on a crystalline structure, right, and have a repeating pattern to them. Water's repeating pattern looks like a hexagon, right? Right here. That takes up a lot more volume, a lot more space when it's ice and frozen and looks like this than when it's water or gas and it looks like that, right? Water is the only exception to the rule, okay? Now, water is special, right? Because at around 4 degrees, right, is when you have a change, when water quits expanding to make ice and starts contracting again with that increase in energy to make water, right? It's special in that way, right? I got a video that shows you that and talks a little bit more about it. Okay? And this is a nice little graph because it shows you what's happening too. Up here in the top right corner, we've got volume on the vertical side, temperature down here across the horizontal. All right? Ice has a big volume, right? As you can see right here. Yeah, because of that open hexagonal structure. All right. Well, then we add some heat, right? And we get right here to this melting point, right? And all those bonds start breaking down. So we go from these open hexagon structures to water, all right? All that space is closed up. That's why the volume drops dramatically, all right? And then in this purple box right here, we can see it blown up, all right? So the volume drops dramatically, all right? But then we start, because those bonds are breaking, but then we keep adding heat, all right? And now those molecules start getting more energy, so now expansion starts to take back over as we heat up, all right? So water's a special case, all right? That's chapter 15 broken down for you, all right? Read your chapter, study up, and if you have any questions, of course, you can always contact me.